Hi, everybody. Thanks for coming. I know it's getting late in the day, so it kind of gets hard to concentrate. But if you make it through this, you get the coffee break, so look forward to that. I'm Anthony. I'm here to talk to you about distributed systems and specifically the inconsistencies, the inherent inconsistencies you get in your data when you move to one of these systems. And with all the buzz around microservices and service-oriented architectures today, this is becoming more and more important. So I work at DigitalOcean, which is a cloud provider of networking, storage, servers, all kinds of good things like that. If you're an email marketing company with Black Friday around the corner and you need something between a hotfix and a long-term code solution, this could be really interesting for you. So we do infrastructure as a service. So keep us in mind for that. But more importantly, I work on the billing team, and I work on everything that's related to making payments and invoicing and anything related to billing. And that's kind of what I want to talk to you a little bit about today, is one of the most important processes in our billing system is our month close processing, where we tally up all the services that our customers have used and bill them for it, and then take any appropriate actions that we need to afterwards. And although my talk is kind of focused on that billing example because it's something everyone can relate to, we probably all have subscription services and things that we use and pay for. It's not, the concepts here kind of transcend that. It could apply to anything where you have some kind of pipeline that you perform one step after another, and you're looking to figure out ways to scale that up and make it more distributed. So this is kind of what our end-of-month pipeline looks like. We have a list of actions that we kind of do for each user, which is like generate the user's invoice, charge them, email them, place an account, holds on the people who don't pay, and then maybe generate reports for our internal users, and then do a bunch of other actions. So there's a lot of stuff going on here. There's a lot of stuff that we do. It's kind of like well suited for this kind of pipeline architecture. And this is kind of where we are, or where we were when I first started, where you kind of have the first step and the second step and the third step. But as we scale up, that becomes really hard to sustain because there's so many actions here. There's a lot of things that we're doing, and they don't necessarily need to be performed in these orders. There's some like loose dependencies here, but we kind of want to turn it into a more parallel system. So this is kind of a slimmed down version of what our actual month close class looks like. So we have the service class called month close, and then we can perform these actions for all these users. And you can see we have all the actions here, but there's kind of a number of different problems with doing it all in one class. A lot of these actions are expensive, like generating the invoice and kind of figuring out what a user has used is pretty expensive to do. Some of these actions have external dependencies, like if we're going to charge you or we're going to email you, we're going to use a third-party service. And some of them are actually kind of complicated. So maybe like we have some complicated logic here that just makes it harder to kind of maintain this class. So doing everything in one big bucket is not ideal. And we also kind of have problems with like idempotency. What if this fails halfway through? Again, maybe one of our third-party services is down and it fails. What happens when we rerun the job? Will we recharge the user? We have some kind of unintended side effect from that. It's hard to say because it's long, complicated, messy. Makes it hard to refactor because you don't want to touch anything. There's like a lot of implicit assumptions there. So enter background workers. This is something that's very handy here, and I kind of want to extol the virtues of background workers. They have a lot of benefits for this kind of work. You can persist the jobs in SQL or in Redis, so as soon as you enqueue a job into a worker, you know it's stored there and it's going to run at some point. You have prioritized job queues, so you can give each worker a different priority, so some might run faster or sooner, and If you have a low priority job, like some kind of report worker or something you don't care when it gets run, then you can set a lower priority. You can do immediate recurring or delayed scheduling. So you can kind of set something to run now as soon as it's possible to process, or maybe later. Maybe you want to get it around to it in a few hours. So maybe you want to send this email tomorrow or something like that. The big benefit for us is there's automatic retries, and you can configure this obviously, but it kind of gives you that free automatic retrying effect where maybe your worker fails halfway through because of a network issue. It'll just rerun again at some point, and once that network issue clears up, you don't have to think about it. You don't have to go in and do anything. It'll just automatically retry for you. And then there's also nice features with like batching, where maybe you might want to run a group of workers, and when all of those complete, either successfully or with errors, you can run some callback. So there's a lot of great things about background workers. And we make heavy use of it at DigitalOcean. So this is what our Sidekick dashboard actually looks like. And you can see we have almost 6 billion workers that we process. And this kind of encompasses maybe like a year of data. And it's probably over that at this point. So we use it a lot, and we kind of wanted to use it even more to scale up. So we use Sidekick, like I mentioned, but there are other background workers out there. Delayed Job, which works pretty well with Active Record and uses SQL and Rescue. So if this is something that's interesting to you, I suggest checking out one of these options. There's a lot of great ones in the Ruby community, and we're very lucky to have them. So I kind of want to run through an example of what this actually looks like in practice to use a background worker if you're not familiar with it. So on the left, we might have our expensive job that's kind of expensive to run, and normally we might initialize it and then run this expensive method. To kind of put it into a background worker, all you really need to do is add another class. And this is an example for Sidekick, but you kind of add this expensive job worker class and include the Sidekick worker, set some of the options here. Here we put it in a high priority queue, and define a perform method that does something. And in this case, we're just kind of passing through the arguments to our expensive job class. So this lets us easily just now run expensive job worker in the background like this. You just kind of set it to run, and it'll run whenever there's availability in the queue. This is an example of doing it in 10 minutes, so just as easy to kind of do that. And you can even do some more complicated things like run it in the background every day. So there's this cool gem called the Whenever gem, which is really nice because you can kind of use this DSL that lets you define some kind of like cron job, and you can run that every day or every hour or whatever it is. And this is actually how our month close worker runs. We have a cron defined that is set to run that month close worker every month for all the users. And this is kind of nice because you keep all that logic in one place in your repo instead of having it maybe defined in a cron file that's defined in like maybe a Chef or a Puppet repository. So you keep all that logic together. So let's kind of apply that to our example so we can do better and take this and then transform it. So on the left is what we kind of come up with now. So when we generate our invoice for our user and we have an amount and we say this is the amount they owe us, we, instead of running the payment and running the email workers in line right there, we kind of run them in the background and we pass through that amount. And on the right, that's kind of what our workers look like. We have the jobs running there, and the good thing about this is that we kind of help solve our idempotency issue from before, because now if our payment worker fails because our payment provider is down, this will just automatically retry. We don't have to worry about it retrying other things that are unrelated to that failure. So that's kind of a nice benefit of doing this. The other benefit is that we can scale things up separately. So Our different third-party providers, for example, might have different throttling requirements, different SLAs, different things that we need to do. So we can actually set throttling limits on all these different workers that are different. And that's really nice because we can scale up as we need to for the specific parts of our system that are bottlenecks. So this is awesome, right? And it turned out to be pretty good because before, when we were running everything kind of in the synchronous class, it took about 30 minutes per user on average. And it took us up to 2 days to finish our whole month close process for all users. So that's really not good if you're like the finance team and you have to wait 2 days from the first of the month to the end of the month to find out exactly what happened with all the money that you're looking to collect. So after about the first day, we'd get like somebody knocking on the door at the Slack channel being like, hey, did we collect the money yet? And we'd be like, no, not yet. Just give us a minute or a couple days. So afterwards, it took less than 10 minutes per user to finish on average because we could scale up a lot easier horizontally instead of vertically. And it actually ran overnight. It took less than 8 hours for the whole month close process to complete, which was really nice because we'd just go to bed and wake up and everything was done. So all's well that ends well, but whoops, this actually kind of introduced a lot of bugs in our system that we didn't anticipate. And I will show you one of these bugs from our help desk right here. So this user wrote into us and says, hey, my account has 2 payments for this month. Can you check again and refund this? Because I came in and paid when I got a notification that I had an invoice, and then later you kind of made a second payment on my account. Like, why did this happen? So that's what we asked ourselves, like, why did this happen? And the answer is kind of obvious once you kind of think about it, but the average time between the steps changed. So previously, once a payment was made, then we'd send the email and handle the failed charge as appropriately. And we had a guarantee between each step how long it would take. It would just take as long as it took for the instruction to move to the next method. Afterwards, we have no guarantee whatsoever because it's in this long queue that may be affected by other things. You might have other jobs in the queue. You might have that throttling going on. So you can't guarantee when something will happen. So now you have this big delay that you didn't account for before, and that's kind of introduced some issues here. So this kind of brings up an important point in that our mental model of what our classes are doing, that's an ideal world. We maybe wrote some nice little stories from a flowchart or something that had like really nice branching trees, and it said like, if this happens, then this will happen, and if this happens, then something else will happen. And it looked all tidy, and we wrote the stories, but it doesn't actually represent how reality works, how our actual workflows work. So like our ideal workflows kind of looked like, hey, the invoice is generated, and then we make a payment attempt. Or the payment fails, and then the user is suspended. Or the payment succeeds, and then the user emailed the receipt. So there's like these and thens that come between each step, and nothing else kind of intrudes upon that. That's just everything in our ideal world. But reality actually likes buts, and I'll pause for your laughter here. Things happen in between each step here that we can't necessarily anticipate. So we might generate the invoice, but somebody on our support team applies a credit before the payment can be made. Or the payment is attempted, but the user goes in and removes their credit card before we realize we can't charge them. Or the payment is attempted, but the user already paid manually. And this is what happened here. The user came in and paid manually before our payment worker could run. So this brings us to our first learning here, which is when you kind of pass information, you're working under an assumption that represents the state of the world at that time. So when we generated the invoice and we said, this is the amount that you owe us, and sent that to the payment worker, that amount was an amount that represented the state of the world at the time that that worker was in queued. It didn't necessarily represent the state of the world of when the payment worker ran. So that was a completely different representation. So this also brings us to the second learning, which is changing methods from synchronous to asynchronous, is an implicit change in behavior. Even though we didn't really change anything about the processing or the order of our processing or what it was doing, like everything still ran in the same order as it did before. We did the same exact steps as we did before. But because the timing was different and because we lost some of those guarantees about what the state of the world looked like, there was a change in behavior. So that's kind of really important to address. So what can we do? We want to do something to fix that. So one of the first things that we thought about was, well, in this case, we need our payments to run immediately after the invoice is generated. So we'll use that queuing priority queue feature in Sidekick and set it as the highest priority. So as soon as the invoice is generated and we enqueue our payment worker, it'll run really quickly, and that will shorten that time from 5 or 10 minutes to something really small. And this turns out to be a bad idea because this is not what you want. If you do this, you're kind of engaging in this priority arms race, and you end up with a queue priority that looks like this. And this is not something that you want to be doing because you'll never really ever solve the issue. Like, you're just kind of kicking the can down the road, and there's always going to be something that's more important. What you want to actually do is assume that the world changes. Like, that's an okay assumption to make. The world will change, that is reality. So we want to account for that. So this is kind of how we want to maybe handle this payment worker, is when we run it, we say, what is this user's current balance? And if the current balance doesn't match the amount we were told to charge, we need to perform some action. Maybe we still charge the user, maybe we throw an error, maybe we do nothing, but this is a condition we need to start accepting as something that's a valid case. And you might look at this and think it's kind of dirty, because that's what I thought too. Like, I was like, well, why should we have to do this? It's like impure. Like, this should just charge the user the amount that we said. And if we can't do that, then there's maybe something wrong with our program or our program design. But I kind of want you to start to think that maybe this isn't such a bad thing to do, because the reality of the world does change, and that is something that we need to consider. So it's not inherently a bad thing to kind of make these checks and try to see how your program can account for that, how your services can account for that. So if you do this, there's actually like a nice little bonus. I think this speaks for itself. I see some confused faces in the audience, so I will explain. But if you've ever seen Terminator 2, this is the T-1000 robot. And he had a really cool feature, even though he was the bad guy, in that when he was shot or encountered some kind of physical damage, he would heal himself. And that's kind of what our program will do if we start to design it taking into account these changes. We'll end up building a self-healing system that's resilient to changes in the environment because we're assuming the environment changes. And this is kind of really nice behavior to have in your architecture, because then you don't have those alerts coming in, you don't have all these errors being thrown, because your services are prone or are resilient to failure. So another thing you can do is freeze your world in time. So we were talking about how the state of the world changes, and previously we had the world looking a certain way at one time, and then later it didn't look like that anymore. So one way you can account for this is doing something like this. So this is kind of what our emails started to look like. Not quite so ugly, but this is a plain text example. But when we send an email to the user, we can kind of say, hey, this is your invoice, and your balance is $10 as of this time. So we kind of froze the world in time for the user by letting them know that their balance was this amount at this time. So maybe they won't get an email and be confused like, hey, I went and paid off my balance, but then I got an email that said my balance is $10. So, this can apply in many other ways where maybe you do some caching, or maybe you display on your website like a kind of a last updated counter or something like that. Basically, you're freezing the world in time for the user and kind of letting the world know you're working under an assumption of what things look like at a certain time. And this kind of reduces confusion and kind of lets you embrace this idea that the world changes. And of course, be a good citizen. So we're in Budapest, so you want to localize all your text. So we account for that here too. So, the gist of all of this is you want to embrace the inconsistency of your workers. Don't try to fight this move from a synchronous process to an asynchronous process, because you're never going to win. If you find yourself kind of doing things to pull you back to something that's a more synchronous, dependable guarantee, take a step back and think of whether you actually need that. If it's something that you need, then you probably need to move back to something that gives you those guarantees. But I think more often than not, you'll find it's probably not something that you actually really need, and that you're just not embracing the inconsistencies that come with moving to this distributed system. And by doing that, you get a lot of benefits out of it. Your services will be much more resilient to failure. You're kind of building this architecture that's more able to withstand the changes in any environment that it's in. So just remember to embrace the inconsistency, because that's kind of the driving force behind a distributed system. So thanks.